wasn't. We'll go from current slide. And turn on the projector. And go over these announcements. I've made these, but, well, let's see. It's not going to current slide. And actually, before I do that, let me back off just a moment. And show you something. Yuck. Yep, it's doing it again. This probably isn't making a lot of sense to you, but this started last week. I think it was Tuesday. Monday classes went fine. They loaded, everything was perfectly fine. Tuesday, Tuesday, the morning classes loaded, but the afternoon classes wouldn't. They would get to 50% and then they would stop, just like this one did here. Okay? And you see I go to retry and it tries and goes back and stops. And then what I have to do is start over again from scratch. So this was on 227, section 12.4. That was not the one I just did today. This is the one from Monday, okay? And it put the wrong thing down here. I corrected it, but it didn't correct it here. That was that one. The other three, I think, did load. In fact, you'll see right here. Yeah, 3 of them loaded, okay? But this one did not, and then the 2 I've done today have not. And here's what the deal is. Tuesday, Wednesday, and Thursday, they all did this. They would load in the morning, but load in the afternoon. So in the morning, I'd load yesterday afternoon's classes. They would upload to to YouTube, but they wouldn't do it in the afternoon. So the next morning, the previous day's classes would do. Well, over the weekend, I thought it was just something here that was causing that. But then over the weekend, I was at a place where really slow DSL, really slow, and it wouldn't do it at night, but it did in the morning. So I think it has to be something at YouTube. I don't know. Maybe they just get more traffic. I don't know. But then it started this week, and nothing, not even the morning classes would upload. So that's why you saw 125, 227, and 238 were last Monday's classes. They hadn't uploaded at all. 112 was yesterday's class. It didn't upload. And then today, while I was teaching 125 and 227, those 3 uploaded, but that one stopped at 50%, and it's not going to do. So your Monday's class is finally uploaded, but it took it until today to do so. And then today's, who knows when it'll upload. I'm going to be, I'll explain the rest of this then as well. Okay, enough of that. It doesn't do any good, so I'm going to just wait. Okay, so let's get back to recording this one, okay, from current slide. I think I tried that before and it wouldn't do anything. There we go. Okay, so let me go over the announcements and I'll tell you part of the rest of what I was talking about. Are either of you in a first mini-term course? No. If you know of anyone who's in a first mini-term course, today's the last day for it. They just last week opened the student course evaluations. They opened it on Tuesday evening around 9 o'clock, and then at 9:21 they sent me something that none of my students had responded yet, as if they could respond in 15 to 20 minutes. I mean, it makes no sense.
They've been slacking recently.
Huh?
They've been slacking with their announcements.
Oh, the awful.
They
Okay.
okay.
So anyway, if you know of anyone who's in a first mini-term class, encourage them to please get the student course evaluation done. They are finally open. I don't know how long they'll leave them open. They usually leave them about a week or so. Okay, so anyway, there's that. But in addition to that, but you are in great shape here. This is my only class where the whole class is in great shape. because as of midnight tonight, that's midterm, okay? We're in first mini-term now, tomorrow starts second mini-term. Midnight tonight is midterm. So sometime after midterm, they ask for us to report midterm progress, which means students who have failed or are failing or passed or D's at midterm. You both have scores in, so no problem. Both of you got your first test in. Thank you, way to go. I will accept your papers at any time, though, and I think you have the second. No, you don't have the second test yet, but I'll give it to you. If not today, I'll give it to you next week, probably today. I don't know if I have enough copies run off, but it won't take me long. Well, I don't have a lot of time. If you can stop me, if we finish early today, then stop me. I'll go down and make the copies, and then we'll get started in the next chapter. But we'll see. But anyway, that's something that happened there. Now, here's what the rest of the craziness of this week is about. Yesterday, I had a doctor's appointment, and this explains some things that had been really puzzling me, but I just thought they were old age. But I have been so tired this term, and especially afternoon classes like this, I just run out of energy. I'll sometimes go down and just get a sipless coat because I'm so tired. Well, I had the doctor's visit yesterday, and he told me I was severely anemic. So I've basically just been running on things until the afternoon. I'll just run out, so that explains part of it. I thought it was just, I'd never been 69 before. I just thought, well, this is what it feels like. But see, I take chemo for a leukemia that I have. I only do a couple of 3 treatments a year because it's a really effective treatment. But it also knocks back my red cells. But most of the time, it's just pretty mild anemia. I've been living with that for years, because of the treatment. But this last time, the one I took in January, must have really walloped my red cells. And it's still walloped, and it's been 3 months. So he's trying to figure out what's going on. He sent me back to the lab to get 5 more blood tests. I had done all my blood draw before the appointment because that's what he looks at. He sent me back to get 5 more tests done so he could see what might be going on with it. So I don't know. Hopefully it won't have any negative effect on the class any more than my just being tired. But it could be that if something happens that, I get too anemic to continue teaching, then we'll have to work out something else out. But I don't feel like that's anywhere close. So hopefully we'll finish this term okay. I'm hoping to finish fall is summer and fall too, and then after that I'm retiring. But I may have to go early if it looks like it's going that way. But he's now put me on, or I'm going to start taking B12, which will improve. He said it's probably not iron because the size or shape, something about the red blood cells indicate it wasn't iron deficiency, but maybe B12 would help with whatever the problem is. So I'll start taking that as a vitamin that helps with that kind of stuff. And I just realized, okay. So anyway, sorry about all that. So all that was done. That was yesterday. Today is a fairly normal day. Tomorrow, I was out missed 2 classes yesterday because of the doctor's appointment and how long it took, and part of a 3rd class. I finished the first mini-term class yesterday, but then tomorrow I'm out again there's a seminar that I have to go to in Tuscaloosa, and I'll be gone almost all day then. Hopefully it'll be over with about 3:30. I'll be coming back this way. I'll stop by campus and I'll be here until 6. So I'm guessing about 4:30 till 6 I'll be on campus. And then Friday I'll be on Birmingham West Campus. Hopefully my full 4 hours, 8 to 12. I do have another doctor appointment tomorrow, but that's Friday, but that's at 2 o'clock. So even if I have to stay late on campus, I can't stay any past 1:15 because I've got another doctor's appointment at 2. So anyway, it's been a crazy week. Hopefully next week will be better. All right, enough of that. Any questions on anything? I know I've taught a couple classes that y'all haven't been here. Hopefully now you'll be able to follow them on YouTube video once they finally get out there. But I finished 2.5 last time, and we're getting ready to start 2.6. Any questions? 2.5 or before. All right. Now, everything we've done in this chapter so far, we've hit separable equations, linear equations, exact equations, homogeneous equations, Bernoulli's equations. You know, just a whole set of different techniques you can do to try to solve differential equations. Okay? But here's how they start this. A differential equation can be a source of information. Of course it is. We started this chapter by observing that we could garner qualitative information from a first-order differential equation even before we attempt to satisfy it. In sections 2.2 to 2.5, we examine first-order differential equations analytically. That is, we develop procedures for attaining explicit and implicit solutions. But get this. But a differential equation can possess a solution and yet may not be possible to obtain it analytically. And in fact, I would say most differential equations are not completely solvable. Now, you can make some assumptions and maybe get them into a soluble form, or sometimes we just have to solve them numerically. And that's what section 2.6 is. And this goes back to something we've done before. This method we're going to look at now is using the tangent line. Now, this is good for first-order differential equations, and it's something sort of we did before. Let's assume that the first-order initial value problem is something like this. Y prime, or dy dx, is equal to some f of x and y. Okay? All of ours have been something like that, generally. And we have an initial point. Y at some initial value x0, we know a value of y0. Okay, there's your initial position. Okay? Let's assume that there is a solution to that differential equation. Now, one way of approximating the solution is to use the tangent lines. Okay? Now, let's just say that y of x, okay, is the unknown solution for this equation. The y prime will give us some y of x that will be a solution. We just don't know what it is. Okay? So here is an example of one. Okay? I don't know why let me just start, because this is going to take pretty much a whole page, so let me start over. Now, here's why I thought it had to do with here, because in the afternoon here, all my lights start flashing. It's sort of like I don't get good, reliable power source. I guess everybody on the system, it just, because even my from the wall, it's solid blue now, but every now and then it'll fade out and stuff. Yesterday, I actually cut out on me. So I assumed it was here. But then it did it at the farm, too. I said, it's not just here. There's something weird going on here. All right, so I'm going to erase all this. And every now and then, you may hear it actually start making a noise because it's not getting a good charge, and I don't know why. So here's what our problem is. Y prime, just like we had before, is equal to 0.1 times the square root of y, square root of y, plus 0.4 x squared. Okay? Now that looks pretty simple, except try solving that. Okay? It's certainly not separable. It's certainly not linear. It isn't going to work on exact. There's no way. It's a pretty simple problem, but there's just no way to get an exact solution. okay, analytically, okay? Now, here's the initial condition, y of 2 is equal to 4. Let's just, well, we can't check and see if that's right, but there's your initial condition. Okay. The nonlinear differential equation in this initial value problem cannot be solved directly by any of the methods considered in sections 2.2, 2.4, 2.5, nowhere. Okay? We can still find numerical values that will tend to work. So specifically, suppose we wish to know the value at 2.5. Not far off from where we started, but that's what we want to know, or at least to have a good estimate of it. Okay? That initial value problem that we have here, that top line here, okay, has a solution, and as the flow in the direction field, and they go back to this again, and let's actually do that. Okay. Here is your XY plane here, and we know that y prime is equal to 0.1 square root of y, is it plus or minus? Plus 0.4 x squared. That's what we know. Now, we know an initial value at x equal to, you know y is equal to 4. X equal to, y is equal to 4. You know that value is there. Okay? So the first thing we do is say, which way is this going from here? Well, this y prime, that's your dy dx, right? And this is 0.1 times the square root of your y value here is 4, plus 0.4 times your x value is 2 squared. So this is 0.1 times square root of 4 is 2, plus 0.4 times 4, right? 2 squared is 4. So this is 0.2 plus 1.6, that's 1.8. So you know your derivative, dy dx, is going up at almost 2. Now, I don't know what slope of 2 is. I probably have it a little too steep, but you know it's heading up at that slope. Okay? So that's going to be our first guess of where this function's heading. We want to get out to 2.5. We want to know what y of 2.5 is. Okay? So here it's heading that way. Well, that's 2. Here is 3. 2.5 is going to be, or this is 3. 2.5 is going to be somewhere here. What is the value when x is equal to 2.5? Well, if we just took one step, we could get an approximate value there because we know an initial point and we know a slope. So we could make a guess. But we can do it in smaller steps and come up to something a bit more reasonable. Okay? So this is called, instead of dy dx or slope, other thing, we could call this our y of, okay, it's not quite a y of x, it's y prime of x, but let's let this be our linearization. They call that L of x, okay? Now, well, okay. Need to fill in a little more gap here. This is your slope. This is your M, okay? So the linearization will have that as a slope. Mx plus, and we need to know a B, okay? Well, let's go back to this first thing that we had, and what is your, when x was equal to, let's see, all right, I'm trying to find where they got their 0.4. And I've done this before, and it's always an elusive thing to know where they got that 0.4. The best I can figure is when x is equal to 1, that would be a 0.4 there. But it should be when x equals 0. So let's see what, we don't have enough information to know. We don't know anything about that. They just come up with this out of the blue, it looks like, 0.4. I don't think that is true, but it is the coefficient here, but why is they use that as a linearization? The L of x then would be, this slope is 1.8 x plus 0.4. What's that?
They find the B for when x is equal to 2. So like,
Yeah, when x,
the equation, the general equation for the linearization.
Yeah.
Like,
okay. If you go back and put that in, yeah, let's do that. If you do the point slope formula, then we have y minus y1 is equal to 1.8 times x minus x1. Is that what you're saying?
Because like in the book, like it says, like after the 0.4 equation highlighted in blue, it says this last equation called linearization of y of x at x equals 2.
Yeah.
So they linearize it at that point. So that means.
Yeah. Well, that's what I'm saying. Let's do that and see what happens. This would be y minus 4 is equal to 1.8 times x minus 2. That would be that, and let's see what we get there. Y minus 4 is equal to 1.8 x minus 3.6, right? Yeah, okay. And then you get y minus 4 is equal to 1.8 x. Well, no reason to write that down again, okay. And what you do at this point, that's exactly right, okay. You add 4 to both sides, and you get y is equal to 1.8 x plus 0. No, you don't, do you? Yeah, 0.4. This is 4.0, 0.4. That's where they get it. Yeah. You plug that point in to this form to see what the line is that's going through that point. Okay. And that's called the linearization. So that's where they get it. Okay. Now, okay. That will be a pretty good approximation for a fairly small change of x, okay? And I wish I could show this on a slope, on the board, but both of you are here, so you're here to see it. If you got your books, they say, let's just assume that's the formula. Here's the point at 2, 4, okay? And the slope is at 1.8, and this is a linearization. The curve is not linear. It's curving. Not curving a lot here, but it's curving some. So for any values fairly close to 2, on either side of 2, that's not a bad guess. It's going to be pretty close, okay? And the method we're going to do is called Euler's method. Boy, Euler hit all over the place. You know the base of the natural number system? What is it called? E. Guess what? And that's Euler. Okay, he came up with that. Okay, Euler was one of the most prolific mathematicians as far as writing papers. Seems like he had like 200 papers that he had written, most of them major papers in his lifetime. How he had time to write 200 papers, I don't know. But anyway, he did. And part of that time, well, I can't remember what happened. He lost the sight of one eye. Okay? And then after a while, he was losing the sight in the other eye. But he could do calculations in his head without actually doing them. And he just had some scribe writing for him, and he was dictating what to do. And he was still writing papers when he couldn't see. He was incredible. I'm trying to think if he's the one or not. I always get him and Gauss crossed up for some reason. One of them was the son of a bookkeeper or something like that. And, Gauss, okay. It may be. And he corrected his dad when he was like 5 years old, said, "You made an error here." He went, "Whoops, what have we got on our hands here?" You know, so that may have been Gauss. Is he also the one that in, like, what was the equivalent to our first or second grade, the teacher got tired of fiddling with the students, said, "Okay, your assignment is to add all the digits between 1 and 100. He figured, Gauss. He figured that would take him a while. Gauss did it in about 2 or 3 minutes. Because he said 1 plus 100 is 101, 2 plus 99 is 101, 3 plus 98 is 101, 4 plus, kept doing down until he got up to 50, plus 51 is 101, and he divided, then multiplied by 50, and he had the answer. You know, boy, these were.
You did it how old?
It was like first or second grade. It's amazing. Yeah, it's just disgusting. I mean, really, it's amazing. But that was Gauss. Euler was just about, I mean, probably was that good. I don't know if he did that much as a young child. But anyway, Euler came up with this method, and basically it's doing the same thing. So it says to generalize the procedure we just illustrated, we use the linearization of an unknown value, y of x, at some value, x equal x naught, and go from there. So I'm going to go back to the previous page, which is here, and our L of x will then be our previous y, which would be y0, okay? Well, later it won't be y0, plus, and then it's your function, f of x0, y0. That basically is going to be your slope. This is the function, f of x, of xy, okay? Times your x0, x minus x0, okay? Now, basically, that's, yeah, I got the wrong direction. That's just what we did here. If you add y0 to both sides, you have y is equal to y0 plus the slope, which is your f prime of x. Y prime of x, which is what they were calling your f of xy, times x minus x0. Just what we did here, okay? That's what we're going to be doing here, and we just keep repeating this each time. So the first time, that's what we get. Our y0 here would be 4. Our x0 here would be 2, and y0, 4. So we just plug those in, and that's where we got our, what was it before? 1.8. No, that's where we got our, yeah, that was the slope. Yuck. And it also does this in the afternoon too. It just shuts off for a moment and then comes back on. This is our 1.8, our slope, because that's your y prime. And it's just y0, which is 2, plus 1.8, that was your slope, times x minus 2. I'm sorry, the y was 4. Plus 1.8 times x plus 2, okay? And that's where we got our first approximation, and that became our y1. So remember, that came out being let's see, what was it? 4 plus 1.8 x minus 3.6. So that was hold off on this for a moment, okay? Because that's just repeating what we just did. So this is, in fact, let me erase this so it's not as confusing. Okay, there is your basic function, your linearization. That's how we're going to get from point 0 to the next guess of a point, okay? All right. Then your L of x1 is going to be, when you increase it by a small increment of h, okay, that's going to be y0, just like before, plus f of x0, y0, just like before. But now your x is going to be x0 plus h minus x0. Excuse me. Now this seems crazy, but it's what the, I can't get my pen to come back. It won't come back. There it goes. Okay. Your x is x plus h minus x0. Well, these go away and it's just h. So this is your next step is y0 plus your f of x0, y0 times h. In other words, your old y plus that little bit of change of dy dx over x, times x, and that gives you a dy. And that's going to increase and be your next y. And that will be your y1 then. That's where the y1 comes from. Okay? So, and they sure can make it confusing. So, this place where x is equal to x0 plus h, you're going to call that x1. And the y that comes out of that is going to be y1. Okay? And y1 is going to be your y0 plus this change of x, change of y with that little change of x, okay, right there, and that's going to be your new one. And then your y2 would be your y1 plus f of x1, y1, okay? There's your x1, there's your y1, times h again, the change. So you just keep increasing it, I'm sorry. They're one step behind, okay? So they make this your y1 being y0 plus h times x1, y1. And then this becomes x2, y2. Yeah. Because this is now your first approximation, once you get it. So in other words, you just start stepping up. Now, the key here is what is your step size, your h, okay? The smaller you make it, the more likely you are to follow the real path, okay? But no matter how small you make it, you're never going to be exactly right, okay? This is really blown up, but here your slope is really close to that. So that's going to do a good job even with a reasonably, not a large h, but with a little bit of an h. Here where the slope deviates more, you're going to have a fairly small h to stay on track. But you still are not quite on track because the curve is always curving. The linearization is always a straight line. So you are going to get off a little bit, and then that's what you use on your next step. So the more steps, okay. The smaller your h is, the more closely you can follow that. You still don't follow it exactly, but the more steps you have to take to get to the same place you're wanting to go. Okay? So your step size does matter. Okay? And as they say here, this is not actually an actual tangent line since x1, y1 lies on the first tangent, not on the solution curve. And that's the key, is because this x1, y1 is now a new point on the linearization line, not on the actual function line. Okay? So that's where your deviations come. Now, this procedure for successive tangent lines, you might call them, it's called Euler's method. Okay? And here we're going to do a couple, and they get a little tedious, but that's why you have calculators, that's why you have computers, because computers can do this much faster than we can, of course. So I'm going to erase this. Okay. Let me just see if it erased my previous. No, it didn't. I'll erase that later, I think. Consider the initial value problem. This is the same one we had before. Y prime is equal to 0.1 times the square root of y plus 0.4 x squared. Okay? That's your differential equation. That's non-solvable analytically. Your initial value, y of 2, is equal to 4. Okay? Now, we're trying to get to y at 2.5. And we're going to use, so our target is to get to y of 2.5. We know y of 2, but we don't know it at 2.5. And we're going to use an h of 0.1. Now that's a fairly good size h, and then later we're going to come back and do an h of 0.05, half the size. Now of course the difference is this will take us 5 steps to get there, this will take us 10 steps to get there. But we'll get awful little less each time. Okay? So here's this becomes your f of xy. It's going to be 0.1 Now, here's something I really regret. Okay, that's going to be our f of xy. Here's something I really regret. Our h is 0.1, but the function itself has a 0.1 in it. Those have nothing to do with each other, but it's going to be so easy to get them confused. Okay? So don't get them confused. Okay? So here is the general equation. Y of n plus 1 is equal y of n plus h. And you see they put the h in front times your f of x sub n, y sub n, and they don't actually put the 0.1 times the square root of y sub n plus 0.4 times x sub n squared. Okay. Now, let's start with x sub 0 equal 2, y sub 0 equal 4. That's our initial point. x0, 2, y0 is 4. Okay? So y sub 1, n plus 0 plus 1 is 1, is equal to 4 plus, now here's the 0.1 here, and this is times the 0.1 there, times the square root of 4, that's your y sub 0, plus 0.4 times 2 squared. Now we've already done this part before. This would be 4 plus, and this part we know from before, well we don't because we didn't have the 0.1. 0.1 times, now let's do this, that was 0.1 times 2 was 0.2 plus, and this was 0.4 times 4 is 1.6, okay? So this is 4 plus 0.1 times 1.8, right? Well, 0.1 times 1.8 is 4 times 0.18, right? 0.1 times 1.8 is 0.18. I'm sorry, plus. I left off my plus. So this is 4.18. So that's our y1, okay? Our y2 is equal to y1, 4.18, plus your increment size, 0.1, times your function, which is another 0.1, times the square root of 4.18. Can't do that one in my head. Plus 0.4. Oh, and by the way, we step up x of 1 is equal to 2 plus h, which is 2.1. Okay? Times 2.1 squared. Your x sub 0 squared. This is calculator time. Okay? (4.18) plus 0.1 times open parentheses 0.1 times 4.18 square root, however you do that, square root, most of your calculators will be square root of 4.18, plus 0.4 times 2.1 squared, close parentheses, equal. And hopefully you'll get a number a little bit more than 4.18. In fact, it will be about 4.4 or something like that. What you get? Or you're taking pictures? Okay. Anyone got a calculator today? What's that? Okay, you don't think your phone will work? I don't know how that handles parentheses. I can't tell you that. That's the only little bit of a problem you might have. Sure you get those parentheses in the right place. when you do a square root, it's going to open another parenthesis. You can do the 4.18 and close that one. And then when you do this one, 0.4 times 2.1, you can just go and hit the square. You don't have to put parentheses there, square. Then you put parentheses after that, and you're equal. See, this whole thing is fairly programmable. What's that? Say it one more time. 4.64. Okay, I didn't get that. The book didn't get that much. It got 4.3768. Okay. Let's see. Wait. Okay. Wait. They first do back and forth, which is sort of a stupid way to do it, with h of 0.1, and then they'll do the h of 0.05, and then they'll go back. They can really get confusing that way. I didn't bring a phone up. I don't have a calculator, so I can't check anything. Let's see, there is a calculator mode on my computer, but I don't know how precise it is. I can't see my screen at the same time. I'm like, well, maybe I can. No, I can't. I don't know. Not worth that. You did have both of the 0.1s in there, right? Okay, 4.18 plus 0.1 times, and that's that parentheses there. You probably need to do a times before the parentheses. I don't know. I don't know the syntax on your calculator. 0.1 is 0.1 times square root of 4.18. Close that square root thing, plus 0.4 times 2.1 squared, close parentheses again, equal. Some calculators will just count
The ones I got,
what you get.
they're not right fitting right now. Trying to get it. I'm trying to get it to just do it in the first one. Up now with that. It broke it down. I didn't want that in there. Like
Do you have parentheses? Yeah, there's parentheses.
it is on there, but it's the buttons are like close, so it
Oh, yeah, I know.
every time I try to get it close, it hits the equal.
Oh, I see. I know. My fingers and thumbs are too big for most phones. My wife got a bigger phone, and she said she was using mine this morning. She said, "You need a bigger phone too," you know, because they are very sensitive. And the calculators usually I can do but better. But anyway, they got a 4.2826. No, I'm sorry, 4.3768. I was guessing it was close to 4.4, but not quite there. Okay? So let's just say that's what we got. 4.3768. Now, at some point, you're rounding. And we're rounding to 4 decimal places. And after that, we got a round-off error that we're promulgating. Okay. So then the Y3 would be 4.3768 plus 0.1 times 0.1 times the square root of 4.3768 plus 0.4 times, x sub 2 is equal to 2.2. 2.2 squared. Close parentheses equal. Okay. Now, if I had a calculator, hopefully I'd get this. I can't guarantee I would get it. While that showed up, let me just put it out here. That would equal, they would say, 4.5914. And then your Y4 would be 4.5914, your previous Y plus 0.1 times 0.1 times the square root of 4.5914 plus 0.4 times, and now your x of 3 is 2.3. 2.3 squared, close parentheses, equal. Okay? They got that one to be, their Y4, to be 4.8244. Okay. So then the Y sub 5 would be the 4.8244 plus 0.1 times 0.1 times the square root of 4.8244 plus 0.4 times 2.4 squared, close parentheses, equal, and they got the Y5 to be 5.0768. Okay. Now, that, if you can trust their curve here, I think they're right here. I don't know, that looks like a different problem to me, because that sure doesn't look like an initial slope of 1.8. That looks closer to 0.8 or 1.2 or something like that. That doesn't, unless their scale's not right, okay? Now this looks more like a slope of near 2. Yeah, I can't tell about that. I don't know if that's even supposed to be the same problem. But to get to 2.5, which would be just a little bit further here, you see the curve is curving up. Our estimate is below it. So the 5.0768 is a little bit below what the actual solution curve is, okay? You might say, how did they get the solution curve? They cheated. Well, no, it's a completely different matter here, okay? Now, kind of hang on to those things. I can't keep them all on the screen because I'm going to try it with the 0.05, but try to hang on to that concept, and I'm going to go back and refer to what we found. Okay, but let's erase this. Ooh, didn't mean to erase it all, but we'll write it down again. When you're using the other, y1 is equal to y0 plus h times 0.1 times the square root of y0 plus 0.4 times x0 squared. Okay? This time we're going to use h equal 0.05, and of course our y of 2 is equal to 4. So our y0 is 4 and our x0 is, y of 2 is equal to 4. Okay. So our y1 here. Now this is a 0.05h. That would be your y0, which is 4, starting just the same, plus 0.05 times 0.1. That doesn't change. That's part of the problem. Square root of 4, which is 2. We know that. So let's just write down our 2 here. Okay. Plus 0.4 times 2 squared, which is going to be 4. So this is equal to 4 plus 0.05 times 0.2 plus 1.6, and this is 4 plus 0.05 times 1.8, exactly like we had before for the first part of that, but now you're multiplying that by 0.05. Someone help me with what that is. 0.09? I believe it is, isn't it? So this would be 4.09. Yeah, that's what they got. Okay. Now that's your y1. Okay, that's the x equal 2.05. Your y2, which is going to be a x equal 2.1, this will be 4.09 plus 0.05 times 0.1 times the square root of 4.09, plus 0.4 times, x of 0 is equal to 2, x of 1 is equal to 2.05. So this is 2.05 squared. So I don't know if you feel okay putting those numbers in. See what you get. Or if you don't want to see what you get, we'll just take it out of the book. They got 4.1842. Now, remember what this is your x of 2 is equal to, okay, I keep writing 4s when I'm saying 2s, I'm writing 4s, okay? What's that?
346. I know you got a class on this one.
Oh, is it?
Yeah. It crimped along.
Okay. All right. Well, you don't have to do all of this, but one thing to notice, you see here, 4.1842. Before at 2.1, we were at 4.18. And you see now we're a little bit greater and we're closer to that curve, but not there, still not there. And so you can look at the 2.2 and then go down and look at 2.2 here, and you see it's a little bit greater, and 2.3 will be a little bit greater than 2.3 was there, 2.4 a little bit better than 2.4 was there, and 2.5 not a lot different, but a little bit better. We don't know what the exact solution is, but I guarantee you the 5.0997 is closer than 5.0768. So anyway, that's it. We'll begin next time with example 2. Okay? And let me get out of this, and I'm sorry if I ran over, but there's no extra charge. Actually,